even though we've talked about a lot of different ways to integrate stuff, we still can't integrate everything. There are some integrals that are just impossible to integrate. And so, for example, e to the x squared dx integral, and then the square root of 1 plus x cubed dx. Yeah, we try to go through all the processes that techniques that we talked about. You're just not going to be able to come up with that. For example, that one, yeah, substitution, you just don't have enough stuff, or U substitution. Parts, so you don't have enough parts either. Kind of the same deal on that. So, through the years, I guess you might say, they've come up with different ways to approximate an integral. We've already talked about some of them, and that, well, one way is how we develop the idea of integral. It turns into the limit of the infinitely many rectangles. That's an approximation of an integral in and of itself if we just use the rectangles. So yeah, if we've got some function a to b f of x dx, just kind of, it's been a while since we've talked about the rectangles. So of course what this means graphically speaking is, yeah, if this is our function f of x, y equals f of x, a to b then is the area under the curve. If it goes below the curve, you got to talk about the net area, but it all works out with the rectangles. Yeah, so we use rectangles by maybe dividing up the a to b into 3, 4, how many ever we want, rectangles, subintervals. Go with 3 here. We call these the x of i's, x of 1, x of 2. Of course, b is x of 3, a would be x of 0. We use 3. And then we decide, if we're going to use rectangles, we decide, do we want to use right-hand endpoints? Do we want to use left-hand endpoints? Do we want to use midpoints? We'll use the midpoint, so I guess I can do that here. So if I use the midpoints, I just come up at the midpoint, and that gives me the height, right, of my rectangle, the function value at that particular midpoint. And then this one, we go up at the midpoint, that gives me the height of that rectangle, and then midpoint, that gives me, so, you get different heights if you use right-hand endpoints and left-hand endpoints, but yeah, the sum of those rectangles then approximates this interval. So the area under the curve, the integral a to b, is approximately equal then to this, we call it a Riemann sum, I equals 1 to whatever, how many ever intervals that we want. And then the height of the rectangles is the function value at each place that we choose, whether it's midpoints or right-hand endpoints, left-hand endpoints, times then this thing we call delta x, which delta x, of course, is the b minus a over n. So that's what we did a while back, right? All sounds familiar, maybe, hopefully. And we will, like I said, we'll use that midpoint formula. I don't think we do any right-hand or left-hand endpoint ones here in this particular section, but they are viable approximations. So that's an approximate integral, approximate value of this integral. Okay, so what are we going to do different? A couple of things. First one is, we're going to call it the trapezoidal rule. And so we're going to do sort of the same thing, except we're going to use trapezoids. Okay, so we're going to take an area. Well, let's first of all remind ourselves of the, we're using trapezoids, and so, usually a trapezoid we think something like that. And on a trapezoid you need big B, little b, the length of the parallel sides, and then you need the height of that trapezoid. And the area of that trapezoid is 1/2 times little b plus big B times the height. Okay? Now, our trapezoids, they're going to have a different orientation. Still a trapezoid because you got parallel sides here. And so our little b, in this case, is here, our big B is here. And then our height actually is that width. This looks like a width instead, but that is the height of that because it's at a 90-degree angle there. And so that's how we're going to compute those areas. So instead of rectangles, we're going to have these trapezoids. All right, well, what does it look like? It looks something like this. So here's our y equals f of x, and then a to b, same integral we're approximating here. All right, but look at this. So if I go up here at a, and then at b, and then 3 subintervals, again, that's x1, that's x2. This would be x3, and this would be x0. And then connect those up too. So here's where the trapezoids come in, because now we're going to connect just across there, connect there, and then connect there. And so we've got 3 different trapezoids, you see. All right? So what's the area of number 1 here, trapezoid? Well, the area of that trapezoid, 1/2 times the little b, f of x, well, let's just do it this way. It'd be f of x0 plus f of x 1, right? Would be the big B and the little b, or maybe I should have put it the other way, but you add these 2 sides, and the length of that side, again, this is y equals f of x. The length of that side is the function value at x0, or f of a. And the height of this side is the function value at x1. And then the height, well, what is the height? Well, again, the height, it's kind of a misnomer here, but the height is actually along here. That's our height, but what is that? It's delta x, isn't it? Each one of these is delta xy, so delta x is actually the height. So that's the area of 1. Well, similarly, 2 and 3, area 2 would be 1/2. It'd be the f of x1 plus the f of x2, right? The height there is f of x2 times delta x. And then a3 is 1/2. It's this one. So it'd be f of x2 plus f of x3 times delta x. And so if I add those 3 up, that is an approximation of my integral. The integral of f of x dx is approximately a1 plus a2 plus a3. Well, look at this. If I add up all those, here's what we're going to have. Let's put the, so we're going to add these 3 up. And if we add those 3 up, notice they all have 1/2 delta x. So let's factor that off. Times, all right, so what do we got? F of x0 plus 2 f of x1s, 2 f of x2s, plus 1 f of x3. Okay. Ran a little room there, but all right. So that's with the 3 trapezoids. 1 f of x0, 2 f 2 of these, and then 1 of the last one. All right, well, I think it's wouldn't be hard to tell there that how many ever trapezoids or how many ever subintervals we want, we're going to have a similar deal. In general, if we do n subintervals, 4, 5, for n subintervals, here's the way it's going to work. The interval from a to b, f of x dx, is approximately equal to 1/2 delta x, or delta x over 2 if you want to write it that way, f of x sub 0. So it's you're always just going to have 1 of the x0, f of x0. Then you're going to have 2 of everything in the middle there. So we're going to have 2 f of x1s, 2 f of x2s, 2 f of x3s, if that's, those are in the middle. So on and so forth, until we get to the very last one, and that one, again, f of x, in this case would be n. That very last one we're just going to have 1 of, okay? And so this is our so-called trapezoidal rule. Okay. Just a little bit different than just regular rectangles, because you got the 2 factors of 2 in there in the middle ones, but that's what it is, called the trapezoidal rule. All right, so let's try one. Use the trapezoidal rule to approximate integral 1 to 4 cosine of x over x squared dx with n equals 5. Use the trapezoidal rule to approximate 1 to 4 cosine of x over x squared dx with n equals 5. All right, so let's start with delta x. So delta x is b minus a over n. So b is 4, a is 1, n is 5. That's 3/5, let's call it 0.6. Use fractions if you want, but I'm going to use the 0.6. All right. I like to also go ahead and write out the x sub i's. You can do it, I guess, in the next step if you want, but what are my x sub i's here? Well, let's start at x sub 0, which x sub 0 is just a, just wherever you start here, so that's 1. And then x1 would be that plus delta x, so that'd be 1.6. X sub 2 then would be x sub 1 plus delta x, that'd be 2.2. So on and so forth. 2.8, x4, 3.4, and then x5, we wind up at our b. x5 is just the 4th, the last one. All right, so then our integral is approximately, by trapezoidal rule, 1/2 of delta x, or delta x over 2, times, I'll write it out, f of x0 plus f of x1, 2f of x1 plus 2f of x2 plus 2f of x3 plus 2f of x4 plus, last but not least, f of x5. So just the first and last one are 1 of them, and the rest of them we have 2 of them. So that's approximately, let's have a little more room, approximately 1/2 of 0.6 times f of 1 to f of 1.6 to f of 2.2 to f of 2.8 to f of 3.4, still can give myself right, plus 1 f of 4. 1 f of 4. Now, then it just becomes a matter of figuring out what each of these function values is. You know, various ways you can do that. You can just plug in 1, cosine 1 over 1. That's not bad. Cosine 1.6. And you can do it by hand. Just a little note here. You can use graphic calculator to do this, or if I plug that in for y, cosine of x over x squared. All right, then go to the, just go back to the normal screen here. All right, so if I put this in, of course that would be 0.3 times, when I've got it entered here, let me just show you this. If I go to, it's under, on the TI-84s, it's under var, or 83s or others, but if you go to vars, and then y vars, what that'll show you is the list of, and then number 1, function. What that'll show you is y1, y2, y3, so forth and so on. And I put mine in for y1, and so if I just hit that y1, or whatever, whichever one you put your function under, the cosine x over x squared, then it puts it back on the calculate screen, let's call it. And if you then do parentheses 1, it'll calculate that for you. And then we can put plus and do this very same thing. Vars, y is a little tedious, I guess, in that sense, but it'll calculate. It'll do all, once we get it entered, it'll calculate it for us, and we can use it to our advantage here. So then we do y1, sorry, 2 of that. 2y1 1.6s plus 2 y1, it's not that bad, but of 2.2, parentheses 2.2, plus 2, ground, vars, y vars, y1 of 2.8, to y1 of 3.4, and last but not least, plus, oops, 2. Last but not least, y1, which is vars, y vars, y1, 4. Okay, so mine basically looks like, what it looks like is it's got y1 of 1 plus 2 y1 of 1.6 plus 2 y1 of 2.2. That's what it's kind of looking like on my screen. I did 0.3 and then did that. That's what mine looks like. I wrote it up there, but you get it looking like that, then it's just a matter of hitting the enter button, and it does it. Negative 0.0522521377. Yeah, okay. All right. So that's the trapezoidal rule. You can do it. You can do that with any number of subintervals. Basically all the same. We'll do another one in just a minute. But any questions on that? Look okay?